In this video, I want to talk about composing two functions, or a composition of functions. Unfortunately, it has nothing to do with writing music or composing anything, but the name composition of functions just means to take one function and plug it into another function. This is the more formal notation of it. Sometimes people call this fog notation because this looks like an O. It's not an O, it's a math symbol, and it's also not a multiplication symbol, so this does not mean f times g. And also, I know that when we have parentheses butt up against each other like this, it usually means that we're multiplying those things. It doesn't mean that either. This is function notation. Usually you see like f of x. Well, now we're just making the function called f of g. And so we say that f of g of x. Even though this is the more formal notation of writing compositions, you might want to rewrite things this way just to help you understand how to do the problem. And this first part in the notes tries to explain this thing about the domain of f and g. It says the domain of f of g is the set of all x in the domain of g such that g of x is in the domain of f, which I think is kind of a really confusing way of saying it. So let's break this definition down. So in math, a function is something that takes an input and spits out an output. You could think of this as a person on an assembly line taking one piece and then doing something to it and spitting out a different piece for the next person on the assembly line. So hopefully they're not actually spitting anything out at the next person, but you get the idea. So let's say we have two people working on this assembly line and they're like putting together shoes, let's say. So let's say person one's job is to take shoes coming down the assembly line and put shoestrings with them. So then when they're done, their output is assembled shoes. So then person two's job is to take these assembled shoes and just put them in boxes. That means that their output would be like these boxed assembled shoes. So I guess in this analogy, this would be f of x and this would be g of x. And we're saying that in order for this to work, the inputs and outputs have to match up. Like in order to get boxed assembled shoes out of this second person here needs to be getting assembled shoes as their input. So it wouldn't work if the output of this function, or like the range of that function, were like toy dolls. So the analogy is getting a little weird here, but if this first person were to take shoes on the assembly line and then start outputting toy dolls, this wouldn't work. We wouldn't be able to get boxed assembled shoes out of this composition of functions. So that's a really important concept to understand, but when we're actually doing composition problems, it doesn't really come up much. So let's try some examples. It says find the following, and it says let f of x be this linear function x minus 2, and g of x is this also linear function 2x plus 1. So number one just looks really weird, but we're just trying to show you that we can write it three different ways. Sometimes you'll just see f of g like that, but that means the same thing as f of g of x, which is the same thing as f of g of x there. So there's just three different ways of writing a composition of functions. No matter how you write it though, the point is to take g of x and plug that into f of x. So like here in f of x, the input is x. That's where we would plug things in. Normally we would plug in like 4 or 10 or a million or 1/2 or whatever, but we're not going to plug a value in. We're going to take the entire function g of x and we're going to plug that in here. So I like to draw boxes around things just to show what's actually happening visually. But let's write this out now. So the first thing I would write in f of x is whatever x is. Well, I'm going to plug this in. So I'm going to put 2x plus 1 in parentheses just to show that I'm plugging it in. And then what do? In f of x, after I plug that in, I have to subtract 2 from it. So just this minus 2. And then let's just simplify this. So these parentheses don't really mean anything right now because this is all just addition and subtraction. So 2x plus 1 minus 2, and positive 1 minus 2 is negative 1. So this is 2x minus 1. Number 2 looks like it's saying the same thing. It's like g of f of x, but the order is different. And the order really matters because this means to take f of x as our input and plug that into g of x. That means I'm going to have to change this around and like change the order of these boxes. So let's take the entire function f of x and plug that in to, well, we would plug things into g of x here where there's just an x. So this big box needs to go right into that small box there. So this is going to be 2 times, think of g as like the big template function. So it says 2 times what? X minus 2 is what I'm plugging in. And then plus 1 on the outside of that. So now simplify this by distributing 2 in. So 2x minus 4 plus 1. And negative 4 plus 1 is negative 3. So 2x minus 3. So look, we got different answers. We got 2x minus 1 over here, 2x minus 3 over here. The order that you plug these functions into each other does make a difference. And here's a weird one. We have f of x. These brackets don't mean anything special. They're just another type of parenthesis or another type of grouping symbol. So this just means take f of x and plug it into the function f of x. So this might be a little unnecessary here, but I'm actually going to write f of x out a second time. It's just x minus 2, but I'm going to write it out over here so we can think of it this way. I'm going to take the input x, and then I'm going to take the entire function f of x and plug it into that input spot. So that means I have to take x minus 2 in parentheses, that's what I'm plugging in there, and then subtract 2 from it. So x minus 2 is just the same thing as x minus 4. And that makes sense. It's like, think of the same function happening twice. This function takes some input and just subtracts 2 from it. So if you took some input, plugged it into the function, subtracted 2, and then plugged it into the function again, subtracted another 2, that's the same thing as just, why don't you just subtract 4 right away and be done with it? I'm actually going to write out a few more examples for us to look at. I know they weren't included in the notes, but they are important in this unit. For example, we could ask you to find, this says f plus g of 3. And it looks like there's multiplication going on, but there's not. What this means, let's actually rewrite it. Again, this is like the formal notation, but how we're thinking of this is just f of 3 plus g of 3, which is pretty straightforward then. That just means plug 3 into both functions and add your outputs together. So up here, 3 minus 2 would just be 1. And over here, if I plugged in 3, 2 times 3 is 6, plus 1 is 7. So then I'm just going to add 1 plus 7, and my final answer is 8. We could also say something like f times g of 1, which I'm going to rewrite as f of 1 times g of 1, which shows us exactly what to do. Just plug 1 into both functions, get their outputs, and then multiply them together. So f of 1 would be negative 1, and g of 1 would be, so 2 plus 1 would be 3. So now I'm just going to multiply those together. Negative 1 times 3 is negative 3. Now let's look at a division example. So this says g divided by f of 2, and again I'm going to rewrite that as g of 2 divided by f of 2. And let's see what happens here. So g of 2, if I plug 2 in up here, that would be 2 times 2, which is 4, plus 1, which would be 5. And then if I plug 2 in here, 2 minus 2 is just 0. So then I have to take 5 divided by 0, and we can't divide by 0. That's actually undefined. So this is kind of a strange example because if you think of these two functions, they're both just linear equations, x minus 2 and 2x plus 1. They're not undefined anywhere. Like everywhere on a line you can find an x and a y value that work out just fine. But if I take g divided by f, there's all of a sudden one value that's undefined. I can't plug in 2 as an input. So our answer is just undefined. In these examples, we actually have 3 different functions that we're working with. So t of x is this table of function values, f of x is written out in function notation, and g of x is this graph. So all these problems are written with some kind of weird looking notation. Let's just do them one at a time. This first one says take g of negative 1. So let's look at the graph and find the x value of negative 1. That's here, and if I follow that down to the graph, its output or its y value is negative 4. So that means I could simplify this inside stuff to just be negative 4, and then I just have to plug that into the function f, which is up here. So f of negative 4 would be 1/2 of negative 4 plus 1. Half of negative 4 is negative 2 plus 1 would be negative 1. So this composition notation just means to take the inside thing, find a value, and then plug that into the outside thing. Alright, the next problem is t of g of 5. So look at the graph where the x value is 5. So x is 5 way over here, follow that up to the graph, and we get an output or a y value, which is also 5. So g of 5 is 5. Now I just have to plug that into t, or the table. So if I plug in x is 5, or the input is 5, that means the output is here at negative 4. So my final answer is just negative 4. These are really just like 2 problems put in one. This next one's kind of weird, but we just have to do it 3 times. So it's just f of negative 10, get an answer, plug that into g, get an answer, plug that into t. So f of negative 10 means I'm plugging negative 10 up here, so half of negative 10 would be negative 5, plus 1 would be negative 4. Alright, so the first step was negative 4. Now I'm going to take that, I'm going to plug it into g. So g of negative 4, let's see what that is. That means look at the graph where x is negative 4 and find the graph. This is a little bit confusing, maybe even hard to see, but there's a hole up here on the graph, so I don't want to include that point. The graph is actually located here at this point 0, so it's negative 4 comma 0. So when I get g of negative 4, I get 0. But I still have to plug that into the table, so this is like t of 0. Looking at the table, the input value is 0 here, and the output value is also 0. So final answer is 0. Next example is t of t of t of 1. So take 1, plug it into t, so let's look at the table, and the input is 1 here, the output is negative 1. So I did this stuff, now I just have to find t of negative 1. So let's do this inside stuff now. So t of negative 1 means find the input of negative 1 here, and the output is 4. So that is 4, so this is like t of 4. So now again look at the table where the input value is 4, and find the output value, which is negative 2. So your final answer is just negative 2. Here let's do g of 2 first. So I'm going to look at the graph and find where x is 2, and the y value also happens to be 2. So this will simplify to just be 2. But I still have to plug that into f, and then on the outside of that there's still a g, and then on the outside of that there's still another f. Alright, so now let's do this inside stuff, f of 2. So plug 2 into this function, that's 1/2 of 2 plus 1. Alright, well 1/2 of 2 is 1 plus 1 is 2 again, so I got 2 as another output. So this simplified to just be 2. So now I have f of g of 2. Well, we found over here that g of 2 was still 2. So if I simplify this, again looking at the graph, the output value is 2. So I finally have to do f of 2, which we already found here. We said f of 2, when I plugged that in, we just got 2. So after all that work, the output value is just 2. And this last problem is a good example of finding an actual composed function. So we're not plugging in any values, we're just dealing with x. That means I want to take the function f of x, and again, we're going to be plugging it into itself. So maybe it helps to write f of x out a second time, which is just 1/2 x plus 1. So I need to plug something in here for the input, and the thing I'm going to plug in is the entire function itself. So using this as kind of a template here, I'm going to write the 1/2 in front, and then what am I plugging in? It's going to be the function again, so 1/2 x plus 1, and then on the outside of this, I still have to add 1. Alright, so let's distribute this 1/2 in there. 1/2 times 1/2 is 1/4, so 1/4 x plus 1/2 plus 1. And then I'm just going to change this 1/2 plus 1 to be 3/2. And that's your final answer.